How are you all today? Welcome to this session where we're going to take a look at high reliability design this afternoon. If you have any questions or comments, please take a look in the chat window and the questions window as well, and feel free to add them in. I will just say I've just had a little panic getting my website up, getting my internet up and running. It's just dropped out. So hopefully now we're through the worst of it and we're good to go. So today, hopefully, we've got a great session. We're going to focus on looking at high reliability design techniques, and we're going to take a look at these of how we can do this using both. To take a look at the systematic level, we're going to take a look at some of the standards, some of the challenges, some of the systematic levels, and then we're going to take a look at the FPGA element of it and try and get that all up and running and working through. And I'll give you some demonstrations. Obviously, we'll make the slides available. We'll make the recording available afterwards. And if you've got any questions or anything, please feel free to pop questions in the chat, which I've just typed a message in now. So if you get any questions as we go through, please put them there, and we'll take a run from there. So let's take a start now. That's what we're going to do. So hopefully you can all see my screen, and there's no issues of anything. But we're going to run through a few sections today. The first section we're going to run through are the challenges. What challenges our system? What really causes our systems to fail? We're going to take a little bit of a look at our standards and the systems that we can use in there. And then we're going to take a look at the systematic level design, some elements of the systematic level design that we can use, and then finally how we can implement those in our FPGAs. So it'll be I hope it'll be quite a good session today, and we should be able to do it. So if anybody's got any questions, anybody's got any comments, just please feel free to pop it all in the chat, and I'll try and answer as we go through. So I want to talk first about some of the challenges that we see in our systems, and they're not always, high reliability systems. They don't always have to face these challenges. They might be medical systems, for instance, that sit in a fairly benign environment, but say failure for them would have a high impact. Whereas we've got other challenges where we face a challenging environment, which can have a significant impact on our devices. So we could have challenges that come to get us. We could be perhaps temperature, vibration, or shock, that dynamic environment. Or it could also be things such as EMC, ESD, interconnection, which is going to cause some issues. And we might be thinking, well, as an FPGA engineer, why do I need to worry about temperature, vibration, shock, and an EMC? And I'll explain the reason why you might have that issue as we go through that. And we're going to take a look at the radiation aspects as well that you're likely to see in a traditional sort of terrestrial application and in a space-based application as well. So hopefully it'll be a really good chat session and pull it through. So one of the key things I want to talk about really at first is the temperature. So our systems really, they have to operate across a wide range of temperatures. And often, actually, when we run at traditionally, it's not always the case these days, but traditionally when we run at a lower temperature, the signals get faster. When we move to a higher temperature, the signals get slower. So that causes us some nice issues, and working across that nice temperature range causes us some challenges when it comes to achieving time enclosure, for instance, in our FPGAs. As well, we also see that actually, while at higher temperature things get slower, and at lower temperature things get faster, at lower temperature we also begin to see impacts from currents increasing, and the power required by our FPGA or by our devices takes more power to do that. We also have to consider startup effects. So it might be actually that at low temperatures we face issues in getting our system to come up and begin to operate properly. So we need to make sure that our oscillators, obviously, and such like our core system fundamentals, are going to at least power up and begin to work. As well as high temperatures, we typically want to limit the junction temperatures of our devices to get the best reliability out of them. So we don't really want to run everything at a high temperature all the time, at its maximum, near its maximum rated temperature, because that's going to impact our reliability of our system. So we want to do derating and lower that junction temperature as much as possible as well. So this is how So hopefully everybody can see, can see me now, and I'm back. I have got no idea what is going off with my internet today, so apologies for that. If it carries on, then we'll try, and we may have to reschedule, but hopefully it'll be good now, and carry on, and we can do that. So what we want to do, really, what I was saying, let me just get my screen up and running again. What we want to try and do, obviously, is we want to try and mitigate these effects of temperature as much as possible. So how we're going to do that is we can select, obviously, we can select parts that are actually suitable for this temperature range. So we can select parts that might be rated for industrial or military temperature ranges. We can derate our standards to make sure that we're not always operating at that junction temperature. And we can use additional qualifying margins when we go to do our qualification. We can use additional margins, such as qualifying against higher and lower temperatures, to make sure that we've got some margin in our system, and we can work there. When it comes to looking at things, we can also work with our mechanical and our thermal team to actually make sure that we get everything working as we want to do, and we've got all the models that show us the dissipation across our system. When it comes to looking at our FPGA, we can also do our timing analysis, and we can make sure that we use the worst case performance in there. So we use not just the best or the nominal, but the worst case performance in there for timing. And we can also put, as you'll see as we move through, we can put additional margins in there to actually begin to help us get some margin and help us close on that, and hopefully pull it together. We also have some effects that come from the vibration side of the world, the dynamic environment. We're going to see some impacts from random vibrations, such as vehicles and in vehicles and aircraft. Maybe they're going to see interactions with the road surface is going to cause random vibration, or turbulence on an aircraft. We also see sinusoidal vibration as well, which is sine waves. Which is sinusoidal things from repeating engines, such as an example of that is a turbo pump, for instance, perhaps on a rocket launch. And we have sound and acoustic vibration, where if we have a large sound, that can be reflected out. It will emanate out from the system, maybe the jet engine or something, and it will reflect back onto the payload, back onto the platform, as it reflects off things. And we'll see that in our electronic boxes as vibration events. One of the key things that we'll see as well is we'll see shock. Now, slightly different to vibration. We'll see shock, which is a short duration, high acceleration event. So you can think of that as a mechanical release or latching, say, for instance, a missile being dropped off a payload, or somebody accidentally dropping the system and working about it. Now, typically, these are going to give us you typically think that these are going to give us an impact that will result in physical failure. But actually, that's not always necessarily the case. So we can actually see vibration and shock failures that cause issues in our FPGA. So, for instance, I've seen a FPGA locking up because bond wires were shorting as it was undergoing vibration, because there was a one-hot state machine that had not been correctly designed, and was going into one of what was actually one of 100,000, because it was a one-hot state machine, illegal states, and therefore the only way to reset it was to go through. So while we do see some of these things as being failure modes, very physical failures, they can also occur during to electrical systems and cause us some issues in our electronics. There are ways we can get around this if we want to. We can take a look at daisy chain devices and building structural and thermal models of this. So early on in our engineering cycle, we can take a look at the boards that we're going to produce, the types of devices that we're going to produce, and we can go and pick these daisy chain devices, and then actually go build a representative model and actually go away and shake it, go away and do some shake, rattle, and roll. And I guarantee you'll see things work, and you'll see some things that don't work, and you'll see some interesting challenges coming out of it. But it will allow you to de-risk your solution and provide a better application as we're moving forwards. And it also retires risk early on in the design cycle, of course. And we all know that the earlier on we can retire that risk, actually, the better. As well as, we have our systems have to operate in an electrically noisy environment. So we share this electromagnetic environment. And ideally, we want to be nice neighbors. So we don't want to radiate too much, which is why we'll go through the stresses and strains and the challenges of EMC compliance. But we also have to be able to accept and live with any radiation, any electromagnetic radiation that might come into our system from other systems that are close by. And we need to make sure that our design is suitably set up to be able to work with that and to be able to see that and not only actually accept it, but actually keep on operating while it's running. So there's some areas that you can see. For instance, we might get corruption in digital words, which we can address in our FPGAs. We might get offsets in our analog signals, in which case our analog team might have to do some clever ratiometric type systems, such that we're always measuring a known quantity and not measuring offsets and such like. And we might get crosstalk in communication systems. So again, we might be as our digital engineers, we might be working with systems to take into account this crosstalk and to correct the issues if we're getting corrupted data. Obviously, in the worst case, if we're working with really high power systems, it could be like my internet today and could be switching off and resetting to its heart's content. So we've looked at the temperature, the vibration, the radiation effect. One effect that always comes into it very interestingly is radiation, and we find radiation comes into it in four. I have got no idea what happened then. It suddenly kicked me out and said there was somebody else on this platform using my name. So anyway, we can get this running through, and we can look at the different types of radiation that we might have in our system. So we have total ionizing dose, and if we're working in a space environment, these are the types of systems that we're going to see. So we're going to see total ionizing dose, we're going to see total non-ionizing dose, we're going to see the one everybody always thinks about, which is the single event upset. So the traditional bit flips, but it's not always just the traditional bit flips that are going to cause this issue. But it could be TID that actually makes us and challenges our design. We've also got deep dielectric discharge, which is a real interesting element, but that's a real system level thing, because that's basically the buildup of charge on ungrounded metal in the satellite. So you want to make sure that that's grounded to prevent any shaking. We can get this. We can also see radiation in the atmosphere. Now, what I'm going to tell you is about this. It's not the excuse for why your board on the desk did that really funny thing wrong once and you can't explain it. But we do see atmospheric neutrons terrestrially as well, particularly as we go higher up in the altitudes and at certain latitudes. We will see atmospheric neutrons occurring, and they will impact. They can impact our design. For instance, if we're flying in an aircraft, we need to take these into account. If we're in a lab, say sat in the UK, in Essex in the UK, we probably don't need to take this into account just as much as we would if we were actually working with that aircraft. Now, when it comes to talking about these things in space, we always, like I say, everybody always thinks about this single event, this bit flip actually. But we have other areas that are an interesting challenge as well. For instance, the total ionizing dose and the total non-ionizing dose of radiation. So the total ionizing dose is a long-term effect. It's just a long-term gradual radiation dose of the components, and it will change. For example, on our digital FPGAs, it will begin to change how that device works slowly over time. It will change its timing performance. It will make it slower. It will change its power parameters by increasing the power dissipation that it draws. One particular thing that I wanted to mention actually, but it's not really for the FPGA guys, but it's for people designing analog circuits or power circuits, is it's actually TID can actually be worse in bipolar and BiCMOS circuits if it occurs at a very low dose. If it's running at a very low dose, then if it's running at a very low dose, then actually the impacts on the circuit of radiation might be much worse than if it actually got the dose at a higher rate. So elders is one that's really critical to look out for when we're looking out for the impacts on our power supplies, our analog and our RF components. Now we do get single event upsets. Obviously, they're the most common types we get, and we're going to take a lot of a look at those in the fourth section, where we look at the bit flips and such that can go on, and how we can protect and mitigate our designs to take this into account. One thing to mention, we tend to focus on the non-destructive ones as sort of FPGA digital engineers. We tend to focus on the flipping a bit, the flipping a bit that corrupts a register, corrupts some data. Maybe if we're really unlucky, it's a single event functional interrupt and resets the FPGA configuration. But we don't really think about the destructive types. But there are actually destructive types of single event upsets that can occur as well. And they can occur predominantly in sort of high current devices, power devices. So you can get events such as single event latch up. Hopefully you don't see this in your FPGAs because you're selecting a sensible FPGA, but we can see things such as single event latch up, single event gate rupture. But the ones as FPGA engineers that interest us are the ones down the bottom, these ones down here, the upset, the multi-bit upset, the functional interrupt, the transient and the disturb. And basically what they're going to do is they're going to change the functionality, the contents of our logic circuit, and we're going to have to mitigate to correct for that. And maybe it's going to change how a state machine works. Maybe it's going to change how the configuration of the FPGA itself is. And we're going to learn how to manipulate that and work with that. So let's take a little bit of a look now at what we've got in terms of the standards that we want to work for when we're working with high reliability systems, because our systems can sit on the ground, they could be in trains, they could be in cars, they could be in aircraft, they could be in satellites, but they've all got to be able to address these challenges. So to address these challenges, there's a lot of standards that exist. And I'm only really going to touch briefly about them. We're not going to spend hours talking about, we don't have hours, but we're not going to spend hours talking about the challenges. We're going to just spend the time just doing a little brief introduction. So there are numerous ones. I guess the two most popular ones that you're likely to come across as an engineer is IEC 61508, which is the functional safety of electrical and electronic and programmable safety systems. It just trips off the tongue, and that's the one that introduces the infamous safety integrity level, the SIL level, and from that there is a number of actually child processes that have developed over the years for specific implementation. So for instance, there's a railway one, there's a machinery one, a nuclear one, and there's ISO 26262, which is increasingly focused on automotive, which is really obviously a hot topic at the moment with self-driving, increasing the levels of automation. You know, this functional safety criticality design comes in really importantly. The other one you'll see a lot of actually is DO254, and that's actually for use in airborne systems. And they're all very similar. While the standards are very similar, the processes that you follow are very similar as well. And I'll tell you, as an engineer working on these applications, when you work with these, you're going to write an awful lot more documents than you're going to write lines of VHDL or design schematics. So what we'll do is we'll take a quick look through. These. And one thing I wanted to introduce is this SIL level, the safety integrity level. You see it goes in increases from SIL 1 to SIL 4. And as you go up this safety integrity level, it increases the time to failure, and obviously decreases the failure in time, which is the reciprocal of the time to failure. So we have a SIL 1 system. We don't really have to do much to it. We don't really have to do much thinking about it. We get about 100,000 hours, shall we say, between failures. But if we want a SIL 4 system, then we need 100 million hours of in between failures. You'll not even find a system that will do this. We'll not even find a system that will do. You'll not even be able to find a single chip that will achieve this time to failure on its own. Never mind when you pull the never mind when you pull the system together. Yeah, apologies. Livestorm's having a few issues at the moment. It keeps kicking me out as a presenter, but I'll keep coming back. So hopefully it'll not happen again. But so we have these 100,000. So we have this 100 million hours that we need to do, and that's a lot to actually get to. So it takes a lot of time to actually be able to design a system with multiple components that's going to achieve that target. We've got a number of areas that we need to consider as well. When we take a look at the safety faction, the SIL faction, you know, we need to think about the failures in the system and how we detect these systems. So we have this function called the safe failure function. And that includes the safe detected faults that we might detect, the safe undetected faults. So a safe undetected fault might be something as simple as a capacitor failing open circuit on a decoupling line. We're probably never going to detect that, but it's not going to have any issues. We might have dangerous failure modes of the system, but as long as we can detect those dangerous failure modes of the system and then take the mitigating errors, we can then, once we've found those dangerous modes, we can find the mitigating issues, and then we can take the action in our system. So those dangerous failure modes are not an issue anymore. What's a real challenge, and what 61508 is really designed around, is trying to find these dangerous undetected modes. And that's a really difficult one, because we don't want to have dangerous failure modes in our system that we cannot detect and we cannot take appropriate action from. So this is the failure space that we're going to be exploring, and we're going to be looking at. So to be able to detect these, you know, we need the safety integrity level comes about as well as a proportion of all the safe and the detected failures based upon the total amounts of failures that we can have. And as you can see, as we look through this, to actually get to these high levels, we need to be able to detect not only a large number of hours and operate for a large number of hours, but we also need to be able to detect a significant safe failure fraction to ensure that our system is safe. And this is going to bring into our design, it's going to bring in hardware fault tolerance, detection and scrubbing and such like, that will make the design work and help us achieve these issues. So one of the things we'll see when we talk about reliability quite often is a concept called MTBF, mean time between failures. And this obviously is included closely with what we've just been looking at. So if we have a common question, actually good interview questions, if we have a mean time between failure of 1 year, does it mean that the system's going to operate without error for a year? And actually it's not, because when we look at the probability of success and we plot the probability of success, what we find is that we're around here for 1 year. So the probability of success of something working with an MTBF of 1 year is about 37%. So this is really interesting, because to get those high failure rates, those high number of hours between failures, you're going to need a very significant MTBF. That MTBF is going to be very high to be able to achieve the rates that we're talking about. So we have a challenge in our system as well. When we talk about MTBF, and I'm not going to talk about this anymore after this graph, but when we talk about MTBF, we are obviously only talking about it during the constant failure rate time as well. So it's only during, so we don't assume infant mortality, we assume that's been removed by the manufacturer via burning, and we don't assume end of life when these components are failing and being worn out. We can, you know, to help us increase better MTBF, as well as doing nice designs and including design mitigation such as redundancy and comparison. We can, if we want, start looking at different quality of components. So we can start looking at QMLV or QMLY is now as an increasingly popular standard as well. So we can look at those and we can put those in. But as we begin to add those into our device, they do add additional challenges in there, because it does come with a significant cost penalty, which is obviously really on some applications you don't worry about it too much. On other ones you want mission criticality, high reliability, and low cost. So it becomes to be a challenge. So we've talked a little bit about the standards. We've talked a little bit about the failure space and such like, and the different types of failure that we can have in our systems. But what are we actually protecting against? So what we're actually protecting against is a couple of types of faults. So we're protecting against systematic faults. So those are faults that occur when we do the design as engineers. You know, we're not all perfect. We make mistakes, we make issues. Or if they occur during the manufacturing, phase as well. We also want to protect our designs against random failures, which occur due to stressors and aging or the environment. So those random failures, you know, they could be anything from an input failing, a pull-up or pull-down resistor failing off and changing the value of an input. They could be transitory. They could be a single event upset occurring. And when we design our systems to do these, we have two options. We can run through the avoidance approach, so we can try to avoid the issue by removing single points of failure, by using the best high reliability products we can, by doing the best design and the best design analysis we can. Alternatively, we can try and make our design to do some tolerance of the design, to be tolerant of that, to be able to be tolerant of that issue as well, and keep on moving through. So let's take a look. So examples of avoidance include doing sort of functional analysis, doing derating analysis to make sure that our components aren't stressed, looking at design rules check, doing worst case analysis, and pulling through those worst case standards. What we can do for tolerance is we can take a look at the system, and we can architect our system to try to be able to detect where the failure in the system is, to be able to localize it, say this is in this element of the system, to be able to limit the failure propagation within that system, to stop that failure propagating outside of it, and then to be able to recover it by using redundant paths. So these are all really important methodologies and techniques that we want to be using in our systems if we go for the avoidance versus the tolerance solution. And we can have this rather nice holistic approach where we can see about how avoidance and tolerance comes together when we're working with the hardware and the software design, and about how it all comes together and pulls together, and what element of the design tolerates that. So avoiding hardware techniques allows it to tolerate software examples, for instance. So this is a really nice diagram. I think that a co-author of mine many years ago on a paper came up with, and it's a really good diagram, I think, for explaining how you can get away with avoidance and tolerance in the hardware and the software domains. Now, there's a lot of applications that we can use to get through this. So we can, to determine failure rate standards, we could take a look at Mill Handbook 217, which is rather old, but there are some other ones such as the Telcordia specification. Siemens have one, and increasingly there are design tools such as Relics and such like, which will also include their own. But a lot of this is really sort of trying to find that information, or going back to the manufacturer and asking the manufacturer for their failure in time, for their analysis, for their data, from their quality program, so as you can actually see what's going off. We have two approaches when we come to analyzing our failure systems and this avoidance versus tolerance. We can do a really comprehensive one called failure mode effects and criticality analysis, and that's going to look through every single event in our design and find that if there's an issue. It's going to be exhaustive. We're going to consider pretty much every component in the design, and we're going to consider everything about it and extend it across to software and the FPGA and everything. The other alternative is we can do the take a fault tree approach, which looks at combinations of multiple events and is really kind of optimized for the design that we're looking at. But it can be a little difficult to perform. You know, the FAMICA can be quite easy to perform, whereas the fault tree analysis requires more understanding and knowledge of the system to be able to work through it. But we can get there, and we can use both of these in our designs. Generally, we find that the FAMICA is really useful as we're working through that detailed design, when we're working through our really detailed design analyses, and when we're working towards preliminary design review and critical design review. The FAMICA is really important, especially down at the component level in that detailed design, when we really want to demonstrate that we've got a safe and approachable system. The fault tree is really good for looking at things at the systematic level, particularly early on, before we've got to the process, before we've got to the really detailed design work that comes with the FAMICA. So it gives us so these two techniques, they're nicely complementary to each other, and they can be used with quite significant benefit to us all. One of the things we can do as well, I'm not going to talk a lot about this, is we can do some derating in our design, so we can work with standards, you know, that we try to reduce the electrical stresses that are on the components. So the electrical and thermal stresses that are on the components, if we can reduce those stresses, a much better system and a much better reliability that can be pulled through into our design. And again, there are a number of derating standards that can be used, from NASA to the Department of Defense to the European Space Agency, and each one is going to be very similar, but they're going to have slightly different tailorings in there to help for their particular needs and desires. So let's take a look now at the system level events, and take a look at some of the things that we can do at that high level to try and get through it. So really, one of the key things to work through in our system to get this design going is we need to be able to put in there redundancy, and it depends on our architecture how we do that. We can run through our architecture and see how we can do that, but we've got to be able to show that we've got two choices with our architecture. Redundancy, we can make it fail safe, which is just detects a failure and stops, or we can, in a safe state obviously, or continue operation such that the system's going. So again, back to this avoidance versus tolerance type approach. We could have active redundancy, in which case we would see no break in operation, or we could have cold spared redundancy, where we have an entirely parallel unit set up and ready to go, but that'll take some time to power up and bring on. Now, when we think about redundancy in our designs, we need to make sure that we don't have any common cause faults, or any common points of failure, any single points of failure, you know, that we can't have any physical propagation between the two, and that we don't have any electrical propagation between the two. Or if we do, it can be isolated to ensure that one unit can't fail, and in its failure affect the second unit and take that second unit out. So in our system, in our FPGA-based system, in our solutions, when we take a look at it, we'll find that the common cause failures are things such as power supplies and power sequencing, their clocks, their resets, their memories and configuration memories, and particularly I/O interfacing as well is a lot of a challenge to look at and run through. And in some instances, we might want to really consider, you know, whether we use components on the same batch or from different batches as well, because that can be quite challenging and impact the design as well. So now let's take a look really what we're here for. Now we understand a little bit about the system, the solution, the architecture, the challenges we face, some of the requirements and standards we might need to work to. We need to take a look at the actual FPGA itself and work out and take a look at the architecture we can do, and some of the tools that we can use, because I do a lot of outside creating demo projects and writing about FPGAs. I do a lot of mission critical design, and one of the tools I use quite often actually is the sponsors of this session, Blue Pearl, and I'd like to show you a little bit about that and how that can help you as well. So one of the key things that we can do when we're designing for high reliability is we want to have high code quality. And what do we mean by that? Is we want to make sure that our design is really, it's readable and maintainable, because it's not just going to be you that's reading this code. Other people are going to be reading it. Maybe the person that's doing the validation, the test benching, maybe the people that are doing the design certification, the design write-off, they're going to be viewing this code as well. So it needs to be nicely readable, nicely presented. It needs to comply with your company's coding standards, and you should really have some company coding standards to make sure that engineers are working in a sensible way. And it's back to this same point again about readability and maintainability. If you've got code, then everybody knows what's going on and the standards that are expected of the code. We want to try and obviously we want to ensure that there's no simulation or synthesis mismatch. We want to make sure that we reduce complexity wherever possible, while ensuring. And once we've got that testability and traceability, what we want to do then is we want to take some specific structures in our code. We want to make sure that our state machines are well designed and that they don't have terminal states or unmapped states. But if we have if long then else chains, we optimize those out because they can impact our timing. We might want to ensure that we've got structural correctness, either that we don't have unused states or undriven nets. And we want to take a look at the clock gating, whether we allow clock gating or not, and whether we've got types that we might want to use as well, such as standard logic or unsigned types as well. So it's a really important thing to allow us to do this code, to have this code quality. Now, if we have this, then we should have some code. We should have some, to achieve code quality, we should have some standard coding rules, and these include sort of making sure that we've got naming conventions, that we've got enumerated types for FSMs, we've got rules on signals and variables, and rules on attributes. We can look at bad coding examples. For instance, we can see this example here where we've got a state type, and we've got it being reset and defined by the left type, the state type tick left, so it's defined by this state here. Now, this is not a great example of coding, because if you change that, if you add to that, the reset state of this changes. And a good code quality tool and a good code checking would be able to check that. So we can pull that through, and we can check that as well. We also want to enforce this code quality. So enforcing this code quality, we can do it personally by doing design reviews and design check-ins. Alternatively, we can use tools such as Blue Pearl's Visual Verification Suite, which enables not only the checking against the LinkedIn standard, so the professional standard, but also against things such as the structural design checks, checking the FSMs to make sure that the FSMs are correct, and doing additional things that we're going to talk about later on, such as clock domain crossing analysis and false and multi-cycle path analysis. And all this is done on the RTL. If you use Blue Pearl, all this is done on the RTL code. It's not actually done after place and route, or after synthesis, or after place and route, or during simulation. It's all done in minutes using RTL, and actually that can give you a lot faster results and help you move into simulation and synthesis with a much better quality of code. And with all those simple gotchas actually found out. So I mean, a few years ago at DAC, Mentor mentioned that about 80% of issues in simulation aren't really functional issues that you find, but they're actually simple gotchas, such as I've locked my state machine up, I forgot to take it out of this state. Blue Pearl can actually help you with all of that. We want to consider our clocks. We want to make sure about our clocks and our startup times. So we want to consider the clocks. We want to consider start times on the clocks. We want to make sure that we carefully use any clocking resources, and we want to be exceptionally careful about clock domain crossing and about how we handle resets that are asynchronous and as they go across clock domains. So we want to look at how we can resynchronize those to the correct clock domain. And hopefully that'll not be too challenging, because the design tools as well, like if you're using Xilinx, then the Xilinx parameterized macros are really designed to help you with these clock domain crossing, and make sure you get your clock domain crossing, your reset domain crossing done correctly, and everything else as well. So the vendors, the people want you to, they provide the tools to be able to do this. It's just being aware of them. When it comes to reset, we want to make sure that our resets are correct. We don't want to rely on the default power up state of the system. For it, there's at least one satellite that failed because the designers relied on the power up state of the system, and it just so happens when they turned on the satellite in orbit, it came up in a different power up state. And it was an image processing application. It got coolant to cool an infrared sensor, and it vented all its coolant accidentally. So the mission was failed. So we can't rely on that power up startup. So we need to make sure that we've got a good clean reset, that our reset takes into account any oscillator startup time plus a margin, and that when we deassert this reset, we're not likely to be causing the reset to occur near a clock edge when it's deasserted, such that we can send downstream devices metastable. It's all nice and simple, but it's all these little things that we can do that pull together that make for a more reliable, a better system. So if we get metastability, obviously we can get this when we do clock domain crossing, and this occurs when we violate essentially the setup or hold times of the flip-flops, and it leads to corruption of data and incorrect behavior. It will go to a, I don't think I've put the picture in. Oh, I have. If we have metastability and we violate this setup or hold time, what happens is the flip-flop will go to a metastable state somewhere in between 0 and 1 before falling out to either a 0 or a 1. And if we don't take into this metastability into our design, into our design, then it can cause a significant impact on the performance of our design. So we need to be able to consider this and make sure that we mitigate it and put in place the correct crossing methodologies. So when we do clock domain crossing, we can do We can do the simple things, the sensible things. We can use a two-stage synchronizer to transfer a single bit of data. Unfortunately, we can't transfer bytes of data using the same approach for a single bit synchronizer, because the data as it moves through the synchronizers will actually become unaligned with each other. So some will be a clock in front of other data, and that will lead to corruption. So we can use a gray code or a handshake synchronizer or even a FIFO to transfer that data from one clock domain to the next clock domain, nice and safe. And I'm going to show you an example about a FIFO in a little minute in Blue Pearl, where we can see that that's an issue, and hopefully pick it up. Yes, so somebody's just put in the comments about the Y satellite. I didn't want to mention the name, but it is, it's a well-known satellite that failed in there, and it's an example of how as design engineers we can have a real impact if we don't think about it properly. So when it comes to doing CDC analysis, we want to run through and make sure that this is all working, particularly if we're working with large FPGAs and we've got large designs with large block designs in there. We want to make sure that we've got all the clock domain crossing correctly sorted and correctly addressed. And that can be a bit of a challenge actually if we don't get it quite right. So CDC issues actually, they're very difficult to find because they change every time you power on the board. If you've got unrelated clocks, the timing relationship changes every time you power on the board, and it might be intermittent, and it's going to be very difficult for you to find in simulation. It's going to be very difficult for you to find in simulation. You're only really going to find it, unfortunately, probably on the bench or maybe even later in the field when it's deployed, which is why using static analysis tools to actually find CDC issues is actually quite a good and powerful example. So I want to quickly show you how you can do this using Blue Pearl, because I think there's a really nice example that I had loaded earlier on, and this is an example of the Blue Pearl. So this is the Blue Pearl development environment. It's nicely graphical. You can script it as well if you want. And Blue Pearl has this interesting ability to work with IPs around the gray cells. So it doesn't actually look inside the IP that we're working with, but it extracts what the first rank of inputs and outputs are and what clock domain they're associated on. So this is a design in the best Blue Peter tradition. This is a design I loaded in earlier on. And if we take a look at the clock domain crossing viewer, I mean, it literally takes a few minutes to load this in, but in the interest of time, if we take a look at the clock domain crossing viewer, what we can see here is we can see a crossing, the tools reporting an unsynchronized crossing between one clock domain and the next clock domain. But the issue is the engineer thinks he's done his design right because he's used a FIFO to transfer from one clock domain to the next clock domain. Unfortunately, however, he's forgotten that the empty signal is related to the read clock and the write clock is related to the full signal. So when he's run his design through and he's created his design, he's actually inadvertently taken the empty signal and used it on the write clock domain, and that creates a clock domain crossing violation. Excuse me. Now that clock domain crossing violation, this is actually a real world example from a real world customer. That clock domain crossing example didn't occur every time, but it occurred often enough that the end customer knew they got a CDC issue, but it was very difficult to track down until you use a static analysis tool, a time analysis tool like Blue Pearl to actually take a look and do that analysis. And that's when, obviously, in a few minutes, if you look at it, you can quite obviously see that there's an issue there, and then go to the code and take a look at the code and correct it. So Blue Pearl is really quite useful in that area. So we have other issues and other approaches that we can take in our designs as well. We can take a look and do sort of TMR, and we can do global TMR where we triplicate everything in our design. And if we triplicate everything in our design, then we do that with the IOs, the inputs, the clocks, the reset trees and everything. And we end up with this rather nice, interesting free implementations in our design. And then to get that to fit in our FPGA, we need to do some isolation, physical functional isolation in our FPGA to separate the free elements. And if we're using a Xilinx FPGA, we can use tools such as the isolation flow to actually give us this isolation between functions. If we want to, obviously, the TMR issue comes with a big impact, and it comes with a big impact. So you may want to take a look at the large grain TMR approach, where we essentially triplicate. We take the same approach as for the overall global TMR, but this time we don't actually do any synchronization between flip-flops. We just vote on the output and take that as the output with our TMR, and that makes our design a little bit simpler, makes our separation a little bit simpler, makes our isolation flow a little bit simpler, because we're not moving from one design from one element to the next. Or alternatively, the lowest element that we can do is what's called local TMR, where we can just triplicate the TMR at the gate level, at the register level, and just do it that way. But then we have some issues with single event upset, single event transients occurring in this area here, close to a clock pulse, in which it gets clocked into the clicked into the 3 elements. So I want to talk a little bit about state machines as well. So we have some, obviously when we design our state machines, we want to be very careful. They are the heart of our FPGAs. Generally, they control the flow of our FPGAs, and we can get issues in there. We can get them going into terminal states, into unused states. We can get the tool to turn on safe state machines, although generally if you're designing for mission critical application, you never actually turn on that option. And we can look at the encoding states as well. We need to think about that encoding state of the state machine. One thing we can do is take a look through take a look at the state machine in the example we've got presented, and we can see here that we've got 3 states, and if a single event transient occurs in any of these 2 states, it's possible to put it into an illegal state, in an unmapped state where there's no recovery back from. And we need to carefully think about how we can design our FPGAs to be able to mitigate that, because the first thing you kind of get taught at university is on a course is you put a when others in VHL, you put a when others statement at the bottom of your FPGA, of your state machine, in case this occurs. The second thing you learn is that the synthesis tool just strips that out straight away and never actually goes away and implements it, because there's no path into those states, so it's not needed. So what we can do is we can take a look at our FPGA about whether we need to do the TMRing of our system, or whether we need to do some protection of our state machine. So we can take a look, and the first thing we ask is do we need to protect it or not? If we don't, really nice. If we do, we need to take a look at whether we want to do correction, so whether we want to be able to see the issue, correct the issue and keep operating, or whether we just want to be able to detect the issue and fail safe. If we want to detect the issue and if we want to correct and keep on operating, then we can do triple modular redundancy and voting of our state machines. If not, then we can use a Hamming distance of 3 in the state encoding to do that. And some synthesis tools will actually do that. So Precision will do TMRing for you. It will do this. Simplify Pro will do global TMR for you as well. Actually, if you ask it to, if you're targeting certain technologies. If we're only going for the detection, not correction, then we can do some more simple things. We can cycle the state machine through unused states at the beginning as it comes out of reset. We can we can actually put synthesis constraints in there to preserve the when others. Although actually, I will admit, in my experience, most design rules and design coding rules don't allow that implementation of synthesis constraints, synthesis attributes in source RTL. Or we can design the state machine to have a Hamming distance of 2 and detect if it's entered a illegal state, and gracefully degrade the state machine from that. If we're working with a one-hot state machine, then we can do the simple thing of we can put a simple parity bit on the end and look at the parity of the system, because obviously at some point in a one-hot machine, only one register should be set at any one point in time. So if we see non-set, or if we see more than one set, we can be pretty confident that we're in an illegal state. So this is what it would look like if we implemented a state machine with a Hamming distance of 3. So for each state, we have a number of adjacent states that also behave the same in the FPGA. And these are the states that the single event, these states just happen to address the single events that can be flipped to by the state value. So we can pull that through. I'm going to stop trying to share on that one. So we can create that, and we can have that implemented. We can also do state machine analysis in Blue Pearl. For example, I recently did an 80-odd state machine for a large demo, and actually being able to visualize it and view it and check that I got it right was quite good. So we can do the analysis in Blue Pearl of our state machines to check that we've got all the states mapped, to check that there's not any terminal states, and to check that we've addressed the design correctly, so we've got the correct power of 2 states used, and that we've not got any inadvertent design errors or design issues in our FSMs. And again, because it's just doing that all statically, it's static analysis, it doesn't take very long for it to run through and be able to do that. It's certainly a lot quicker than waiting 8 hours for a simulation, so only to find out that you've popped it into an illegal state. We also want to think a little bit about our counters and how we design our counters. We often don't want to just check the count for the terminal value. We might want to check the count for being greater than or equal to the terminal value, or less than or equal to the terminal value if we're doing a down count. And that gives us the ability to not end up in a locked up state where the logic's looking for a specific value, but that value never occurs. Putting elements like this in, they might affect your design, and they might affect how your system is behaving because a count terminates early or something like that. But that's a system level issue that can be recovered from, and it's a lot better than the system actually locking up and it being unrecoverable. One of the other things we can do as well is we can put watchdogs in there to help us check for single event functional interrupts, to make sure that we're not getting locked, that we're not locking up, or that the FPGA's not just sort of had a single event functional interrupt that's erased its entire programming if we're using a SRAM based FPGA. And while you can integrate it in the FPGA, it's better if you're going to use a watchdog approach to use a discrete one externally. Otherwise, it becomes a little chicken and egg and introduces a common mode of failure considerations. So with about 5 minutes to go, I must apologise for the few technical problems that we had at the beginning with Livestorm kicking me off quite often. But we've taken a look all the way through the design process, from the challenges that we face to the standards that we might work with, to some of the system level aspects that we might want to consider in terms of reliability, in terms of redundancy, and to some of the FPGA design techniques that we might want to look at, such as making sure that and they are very simple because the best things in life are, making sure that we've got really good coding standards, that we enter into our designs with the best quality of into simulation synthesis with the best quality of code that we possibly can, making sure that we've got sensible clocking, sensible reset strategies. We've analyzed our design to make sure we've got no clock domain crossing elements. We've considered whether we want to have a large-scale TMR or a global TMR or a small TMR, or even if we just want to TMR small elements of our circuit. We've also taken a look at what we can do with the basic structures that we put in our FPGAs that we use every day, such as state machines, and how we can protect those state machines or detect the issues in state machines, and how we can take out the counters and protect the counters there, before finally looking obviously at the last element of that. So if you've got any questions, please pop them in the chat, and I'll try to read the chat. I've tried to read it as I've been going through the presentation, but it's a little difficult and a little off-putting. So somebody was just asking actually if there's any good books or white papers that talk about good RTL practice. And one of the best I know, actually, if anybody wants to email me, I'll share this link, or I'll find a way to put it on the comments on the YouTube video that we put up. But there was a DO254 VHDL working group a few years ago, maybe actually going back 10 years, and they actually created some really good coding practices for both code quality, for both readability, code quality, synthesizability, and place and route. And unlike everybody that tries to do this, they were actually really sensible, and they kept it to a small, unique group of rules for everything, so that the rules would be complied with because they weren't too onerous to do it. Another set of rules actually that's quite good to look at on this is actually the French Space Agency, so the CNES, has a set of rules that are publicly available as well on RTL code quality and what to implement in code quality. The European Space Agency doesn't quite have a standard of rules yet, and I know that because we're working with Blue Pearl with to look at some ESA codes. I'm using Blue Pearl to look at some ESA IP cores and checking them. But what they do have is they have a handbook about high reliability design that's also free to download. And I will pop those links whatever we do with the video, we will pop those links in there. So somebody's just asked a really interesting question about if I think HLSC is good enough for high reliability. And I think that's a really interesting question. It's not something that I have done a huge amount with, but I think there are definitely opportunities, and it's a thing that we should be considering and looking at, is the quality of code these tools come out. And I think there's a really good research project in there actually in looking at how you can use the pragmas that HLS tools offer to actually give the best results out. And I think, to be fair, I think initially if you were creating HLS blocks in C, and you were doing some sort of triple modular redundancy and triple modular voting on the output, then that might be good enough. But obviously each application changes as to what the overall sort of certifying authority is happy with and would do with. So somebody else asked a question saying about safe FSM encoding of synthesis tools is normally not allowed, and it is kind of a little bit counterintuitive because you'd think it's what we want to do, you know, safe FSM encoding. But if you think about how that works is you're allowing the synthesis tool to go away and put in additional logic that looks at your state machine and can actually reset your state machine to a known state should it think that the state machine's gone wrong. But that logic that also gets added in is also subject to single event upsets and errors and such like. So it's possible that you could see errors in that additional logic that would impact your state machine, which is why it's better to actually design the state machine from scratch to take into account and to do those mitigation techniques that you want to do, such as running through the reset state, so implementing a Hamming state of 1 or 2. So somebody was asking, is there a good way to calculate reliability for RTL? FPGAs can only provide fit rates. So it's obviously the FPGAs, the base fit rates. I mean, I think for like Xilinx 7 series, the fit rate for the FPGAs is 10 or 12 fits, something like that, according to their quality guide. What you need to do, what I've done when I've worked on sort of SIL4 projects in the past for high reliability FPGAs, is we've actually gone through and essentially done a what they call it now is essentially done a failure mode effects and criticality analysis inside the FPGA itself. So we would analyze the FPGA blocks in the FPGA and say, how does this block behave if this input gets stuck high, if this input gets stuck low? How does this block behave? What's the effect? What's the next end effect? And you can begin to pull all that information through into your overall FMICA process and do that analysis. Sorry, Hans, I'm not sure about your comment about using double bit protection Hamming code. Was that in relation to something I'd mentioned or not? Right, yes. So somebody was asking, do we have the same rules when coding for HFT? So are you talking hardware fault tolerance systems, or are you talking high frequency trading there, Sandeep? But I'm going to assume you mean high frequency trading. So that's an interesting question, because high frequency trading is not necessarily mission critical. Nobody's going to die at the end of the day if an order's not placed in time or something. But again, you want a high availability, you want a high update. So some of these solutions which can give you a good availability, a good update, and make sure that your system availability is up and running, certainly you should use them. But I assume as well with high frequency trading as well, you've also got one eye on the latency as well, and minimizing the latency. Any other questions? I can see someone typing, so I'll just. Oh, so that's a great question. Is there any advantage in using synchronous or asynchronous resets? You're going to have to read the documentation on that. And what I mean by that is you're going to have to read the documentation for whichever FPGA you're targeting. Some families, for instance, some families will recommend that you use an asynchronous reset. Some designs will recommend that you use an asynchronous reset. And it really depends on the architecture that you're implementing in your design. Even if you use an asynchronous reset, you should try and make sure that asynchronous reset is deasserted in a safe manner, in a safe manner in relation to the clock domains. But particularly, I mean, take a look. The Xilinx ultra-fast methodologies actually is a really good book. Is a really good user guide to read, and that'll explain to you about the Xilinx ecosystem of the benefits of using the differences between using a synchronous or an asynchronous reset, and how it ties your hands in the Xilinx FPGA world. So Nigel asked an interesting question about the difference between 61508 and DO254, and they are. It's like everything. They are both are very process driven, both very interestingly done. One of the most interesting differences between the two is in 61508, you can have this concept of a qualified tool. So your tool can be certified for that for certain safety implications and safety levels. You can't actually do that for DO25. You can't do that for DO254. I can see lots of people typing questions here. So this is a really good question actually about the there's a really good question about the difference between high reliability brands such as Xilinx or Microsemi. Although I write a lot about Xilinx devices, I actually use quite a lot of Microsemi devices as well in my engineering consultancy, my private practice. And it really depends upon the applications that you're currently designing for and developing for. Obviously, with the Xilinx FPGA, it's an SRAM-based FPGA, so you have to take into account the consideration of the impacts on the single event upset, or even actually the configuration time that it takes for the FPGA to load its configuration from the boot memory. The configuration time can be an issue if you've got really tight challenges in terms of power on to being able to send responses. But the corruption of data in memory is not so difficult because that can be mitigated by using things such as the single event mitigation IP and understanding the Xilinx essential bits technology, which will tell you roughly the number of bits in the bit stream that are likely to be impacted by single event effects. If you take a look at the FPGAs, you'll tend to find that for space probes, as Hans is saying, you'll tend to find they do actually use Microsemi devices, mostly because they're generally either one-time programmable or flash based, so they're live at power on, and they're seen to have less impact on the less reliability impacts due to single event transients and the configuration data being put in there. It's not a view I actually think is I actually hold. I think you pick the best FPGA for the mission at hand. I've certainly designed telecoms processors using large Xilinx Vertex 5 QV FPGAs, and we've been able to get them to behave as we want. So it's like everything. It comes down to picking the right. You're an engineer. Your job is to look at the requirements, look at the environment, look at the challenges, and to actually determine which is the best technology to use. And you know what? Sometimes it might not even be an FPGA at all. Maybe you should actually, maybe while the customer said we want an FPGA, maybe you should go away and do it with a processor or something, because it'd be more sensible to do. Okay, any other questions before we wrap up, guys? So that's an interesting question. How do you verify hand-coded SEU mitigation logic? So you can do that by simulation. ESA has a little script on its website as well that will run through that will do working with model sim. We'll kind of inject single event upsets in there, which is quite cool. Or you can take it to you could do some testing on it, or you could do formal equivalence checking or something on it as well. So there's an interesting question about whether these things are process driven because there's no direct way to estimate the calculability of RTL. It's not only that, I don't think. I think it's the main reason that they're so process driven is by doing humans make errors, humans make mistakes. So by having processes and making people follow a process that people can actually repeat, that can actually understand where they should be in the process, what steps they should be taking at that point in time, and what they should be doing, what the quality looks like, and put into all the sensible steps and checks. So Graham was just saying, what about the new crop of rad-hard or rad-tolerant FPGAs? A lot of distinction. Of the distinction of that. Yeah, so there's a lot of, there is a lot of rad-tolerant FPGAs out there at the moment. There's a huge range of them. There's the ESA Brave FPGA, the European space grade one. There's the Macrosemi have released quite a lot of Pro ASICs and rad-tolerant Pro ASICs, and the PolarFire ones that are all capable of working in these rad-tolerant environments. So there is a range of them, and it's certainly an interesting area to look in, and we could probably fill another hour's discussion on that. I think the main thing that's exciting about them, to be honest, is just how just how more modern they're getting. So for many years we were looking at things like the RTAX from Actel, maybe some small Xilinx devices if you wanted a little bit of high programmability. The Vertex 5 QV was a really great device, but it was really power hungry. But now you've got some really great devices. You've got the Pro, you've got the Pro ASIC 3. One of my flight missions were flying the Pro ASIC 3 rad tolerant. You've got the RTG4, which is actually a really high performance Pro ASIC flash based FPGA. You've got the new ones that have come out with the PolarFire. With the associated processors that can probably be dropped in there as well. And of course, you've got the new Xilinx Kintex devices, Kintex UltraScale devices, and I'm talking to a client about who's using those at the moment. And it's really quite exciting. There's a lot of devices out there, a lot of exciting things that can be used. So somebody's last comment is putting there about what about including lessons learned as well. Lessons learned are great. At the end of every project, everybody always sits down and writes, on the next project we will do X, we will do Y, we will do Z, and then they put that in a filing cabinet or file it somewhere on the network, and you don't see it again until next time round when you go through the next project and you sit down to the lessons learned again and you say, we'll learn this lesson, this lesson, this lesson. So actually, lessons to be learned, a better term, actually lessons to be learned, to make sure that actually people do actually go away and learn the lessons and actually listen and learn from what's gone off on that particular development process. Because I don't know about you, but I don't know about the people attending, but I always learn everything as I'm working through this. I tend to always learn new things as you're working on projects and moving through. Any other questions? Well, if not, I will thank you very much for obviously coming along and spending the hour and a little bit with me, and we'll meet again. I'll put this. I'll do some editing to perhaps edit out some of the cuts that we were taking with the internet playing up and down. I'll do some editing, and we'll pop it on. I'll pop it on YouTube or something, and I'll put the links to the tools and to everything we've mentioned today. I'll put those in the comments below. It's been my pleasure, guys, to do this. I do actually run a 2-day course on this, so if anybody's company's actually got any budget and would like a detailed 2-day course on high reliability design for FPGAs, I'm just teaching it to the Australian Department of Defence at the moment. Then please drop me an email and we'll see what we can do.